We will now continue with our discussion on PV diagrams that we started in the first part of the lesson. Tell me, what does a PV diagram represent? Well, it is a plot of pressure against volume, and the area under the PV diagram represents what? It represents the work done. Okay, now here I have a situation. The figure here shows an ideal gas at a state P1, V1, T1. So at this point, the state of the ideal gas is P1, V1, T1. It now moves to a state 2. What is the state of the gas here? Pressure remains a constant. Pressure hasn't changed. Volume has changed to V2 and the temperature has changed to T2. Alright? So the figure shows an ideal gas at an initial state P1, V1, T1 and heated at constant pressure to a state P1, V2, T2. What is the work done during that process? The work done during this process is the area of the shaded region, which will be this pressure multiplied by the change in volume. What is the work done for an isobaric process? This stage is an isobaric process. The work done is pressure multiplied by the change in volume, PdV, which is the area of the shaded region. Now, the gas is now cooled under constant volume. Look at this. It is cooled under constant volume so that the pressure reduces to P2. The volume remains a constant and the temperature falls to T3. Tell me, what is the work done during this time? From state 2 to state 3. What is the work done now? Well, there is no work done. Why? Because work is done only when the volume changes. Since there is no change in volume there is no work done. So the work done during this stage is 0 since there is no work done. That means when a gas is taken from state 1, that is P1, V1, T1, to state 2, P1, V2, T2, to stage 3, P2, V2, T3, the work done is given by the area of the shaded region. Moving from state 2 to stage 3, there is no work done. Therefore, the total work done is the same as the work done during the first change. Okay. This figure shows the ideal gas. Now, let's go through another situation. Here is another situation. A gas is at an initial state, P1, V1, T1. It is taken through constant pressure. It is cooled at constant pressure to a state P2, V1, T2. Alright? From an initial state P1, V1, T1, the gas is cooled at constant volume to P2, V1, T2. Pressure changes from P1 to P2, volume remains a constant, temperature changes from T1 to T2. Tell me, what is the work done during that process? There is no work done. Why? Because there is no change in volume. Alright, now it is heated at constant pressure so that the state now changes to P2, V2, T3. Now, what is the work done during this time? Work done is the area under the graph. So the work done during this process is the area under the graph, and this is the total work done. If you notice, In the previous case, we took a gas from P1, V1, T1 to P1, V2, T2, and then to P2, V2, T3. It reached the same final state. The final stage in the previous case and in this case are the same. But in the previous case, you notice that the work done was a large quantity. But in this case, the work done is a very small quantity. So the path taken in a PV diagram is very important as far as the work done is concerned. Let's now talk about isothermal expansion. What is an isothermal expansion? What does isothermal mean? Well, a process that takes place at constant temperature. So an expansion, a certain amount of gas is allowed to expand at constant volume. Now, suppose I ask you, well, I want to ask you this question. What is the equation for an isothermal process? We derived an equation for it some time ago. You remember, Boyle's law deals with isothermal process. What is the equation for Boyle's law? Boyle's law equation is P times V remains a constant when the temperature remains a constant. Well, when we talk about isothermal change, we don't need to say temperature remains a constant, because for an isothermal process, the temperature is a constant. So the equation for an isothermal process is P times V remains a constant. That is the equation for an isothermal process. I will ask you this again in the next class. Okay. Now, this is the picture that shows an isothermal process. The temperature remains a constant. You can see the initial state of the gas is P1, V1, T1, and it expands from an initial volume to a final volume at a constant temperature. The temperature does not change. The pressure changes from P1 to P2. In other words, the pressure falls. The volume increases, the pressure decreases. You remember this curve when we talked about Boyle's law? What do you call this curve? This curve has a name. This is the isotherm. So this is the isotherm of this gas that expands from a state P1, V1, T1 to a state P2, V2, T1. What is the work done? The work done is given by the area under the graph. You see, previously it was easy for us to calculate the area because the areas were rectangles. This is not as easy as that. So what do we need to do? We need to use the method of calculus. Since the temperature remains a constant, such a process is called an isothermal process. The work done in an isothermal process is given by the area under the PV diagram, and I can write it as, how can I write it? It will be integral V1 to V2 of PdV. Well, the same equation. Work done is integral V1 to V2 of PdV. But what is the difference? In the previous case, we considered the pressure remaining a constant, isobaric process. When the process is isobaric, the pressure remains a constant, that line will be a straight line. So you don't need calculus to measure that area. But in this case, you need to use calculus because pressure now is a variable. Volume is a variable and pressure also is a variable. So if you want to do this integral, you need to rewrite this pressure in terms of V. Can we do that? All right, let's see. We can go to our savior. You see the gas equation. PV equal to nRT, and we can solve for P from there. What happens? P equal to nRT over V. If you notice, nRT is a constant. Isn't T a constant for an isothermal change? Yes. So, because the change is isothermal, T is a constant, R is a constant, N is a constant. So, we now expressed P in terms of V. Let's take this value of P here. Therefore, what is work done in an isothermal process? Replace the P by nRT over V. Will be integral V1 to V2 nRT over V times dV. And we can now take the constant terms outside. nRT is a constant. So that will be nRT comes out integral V1 to V2 of 1 over V dV. Okay, how many of you recall this integral? What is integral of 1 over V dV? It's a very elementary integral that you do in your calculus 1. Is that right? Integral dx over x is ln of x. Integral of dv over v is ln of v. I hope you know that. See that? But integral of dv over v, so this is the standard integral. Integral dx over x is ln of x. Therefore, integral 1 over v dv is the same as dv over v is ln of v. So, this integral is ln of v. That is nRT ln of v. Lower limit is v1, the upper limit is v2. What do we now do? Set v equal to v2, the upper limit, and then minus set v equal to v1. That will be nRT ln v2 minus ln v1. And use the properties of logarithms to write this as a single ln quantity. What is ln v2 minus ln v1? That will be ln of v2 divided by v1. And here is another important equation that you cannot afford to forget. Work done in an isothermal process is nRT ln v2 over v1. Take note of that. Work done in an isothermal process. Alright, let me ask you now, what is the equation for the work done for an isobaric process? The pressure remains a constant. Is P dV, P times V2 minus V1. Work done in an isothermal process, temperature remains a constant. Is nRT ln V2 over V1. Okay, let's do a small problem.